So our first question was a lot about mechanics and a lot about some forces. All right, so let's take a look at question 2. Again, I'm going to start by reading this first bit up here. All right, that gives us context for the rest of the question. Okay, so we might need to use this information multiple times. We've got a mass 55 kilogram athlete. Okay, we've got some context which we might need to talk about. Okay, so we need to get it over our crossbar without hitting it. High jump. When she lands, a padded mattress cushions her fall. So, part A, calculate the size of the forces, so possible plural, acting on Sarah just after takeoff. All right, now they don't have, I can't get the diagram, okay, so we would have a diagram, but we've got to calculate the size of the force, so that's step 1, and then we've got to draw arrows in the box. We basically got to do a force diagram. Okay, so just after takeoff, all right, if she has just taken off, she will not be touching the ground anymore. Okay, so there will be no force, sort of support force provided by the ground in any way. Okay, so what we're going to assume is that the only force that is happening is the weight force. Okay, so we've got given our mass of 55 kilograms, and we've got our gravity on our resource sheet as 9.8 meters per second. Okay, so we just have to times those two together. 55 times 9.8, and we get 539 newtons. Now, this isn't our final step here, because we need to look at our significant figures. So, 55.0 kilograms is 3 significant figures, okay? But our gravity is only given to us in 2, 9.8. So our answer must also be 2 significant figures. So 540 newtons to 2 significant figures. Okay, now we've done step 1 of our question. We also need to do step 2. Draw an arrow or several arrows in the box to show the direction of the force. Okay, so we should just have a single arrow pointing down. Okay, now that gets us to our achieve. That's our first question. Gets us started off. So our second question. During one of the jumps, the initial velocity of Sarah, so that's important, VI, at takeoff is 8 meters per second. At an angle of 70 degrees to the horizontal, and they've got a diagram here for you. Okay, calculate the time it takes for Sarah to reach the maximum height in position 3 above. Okay, so we know a few things about this. We know that we're going to be working in the vertical. Okay, we're going to need the up and down because we want a maximum height upwards. Okay, so that means we're going to need to get the vertical component of the velocity. Okay, so the way we do that, all right, is we work out our triangle, okay, and then we can do SOHCAHTOA. So what we're wanting to work out is this bit here, okay, that part of the velocity. We've got our hypotenuse, okay. We need to have a useful angle, okay. So we get given the 70 degrees, all right. Now, in this case, this is our opposite, okay. We've got our hypotenuse and this is our opposite. So we're going to be using sine, okay. Right, this is our so. We've got our opposite and our adjacent, and we need our sine, okay. So, to get our opposite, we need to use our hypotenuse, which is 8.0, times by sine 70. Now, be careful to check that your calculator is in degrees. Okay, so 8 times sine 70, and that gets us to a vertical velocity of 7.5 meters per second. Okay, so we've got a velocity that's now in the vertical dimension. Okay, we need to work out the time it takes to get to the maximum height. So we have two other bits of information that don't necessarily get given to us in numbers in our question. Okay, we have an acceleration. Because we're in the vertical component, we have our acceleration, which is gravity, so 9.8 meters per second squared. Okay, we also have a final velocity. So remembering that at the very top of any projectile motion, okay, just for that moment right at the top, the velocity is going to be 0 meters per second. Okay, so, and we're needing to work out our time here. So we've got an initial velocity, an acceleration, a final velocity, and we need to work out time. So what we do is we get our resource sheet, and we have a look at our projectiles. Okay, so we don't have a distance, so we can't use any of those. All right, we're going to use this one. VF equals VI plus AT. All right, so I like to rearrange using the letters first and then substituting the numbers in. So VF equals VI plus AT, and we're wanting to get T by itself. That needs to be our subject for this one. Okay, so what we need to do is we need to rearrange this. Now our first step is to shift VI over to the other side. Okay, so because it's plus here, the relationship between here and here is an addition, a plus, we're going to need to minus it to get it to the other side. So VF minus VI is equal to A times T. Okay, now I'm sure you can see from here, we're just going to divide by A. So VF minus VI divided by A gives us our T. Okay, so that's our rearranging. Now we can just substitute some numbers in. Now I'm just going to flip this equation around just for ease of reading, but it does mean the same thing. So T equals VF minus VI over A. All right, now our VF is 0. Our VI, we worked out using trigonometry, was 7.5. Okay, and our A is our gravity, so 9.8. All right, so all we need to do is substitute, put that into our calculator. So 7.5 divided by 9.8, and we should get a time of 0.765 meters seconds. Now, remember our significant figures, so we get 2 and 2 and 2 here. So we're just going to be working in 2, so 0.77 seconds. Now, you'll notice that 0 minus 7.5 would actually be negative 0.5, okay? But what we have done is there's actually also a negative here. So that's telling us the direction of our acceleration, okay? Remember that negative has two functions. In physics, it's a negative number or it's telling us a direction, okay? So because we have two negatives here, all right, if we did that in the calculator, negative 7.5 divided by negative 9.8, okay, we get the same answer. Two negatives divided by is a positive answer. Okay, so we end up with 0.77 seconds to two significant figures. Okay, so if we get just to here, working out that it's trigonometry and we get to 7.5, okay, we can get an achieved. Or if you somehow get this one wrong but you do end up with this, you can still get an achieved. Getting this whole working correct and getting this step correct before you get to here will get you to a merit. Okay, so after Sarah has jumped, She lies motionless in position 4, as shown on the diagram. There are 20 springs evenly spaced in the area of the mattress where she lands. The average compression of each spring is 4.5 centimetres and Sarah's mass is 55 kilograms. Okay, so our question is calculate the elastic potential energy stored in a single spring of the mattress. So we're just looking at one spring here. Alright, so we're looking at elastic potential energy. Okay, and it's the potential energy just in one spring. Alright, so eventually we're wanting to use the equation EP equals half kx squared. Okay, we do have an x, right? That's our distance, that's this 4.5 centimetres, but we don't have a k. Alright, so we need to figure out the k, or the spring constant of the springs first. Okay, so to do that, we have our Hooke's law, F equals negative kx. Alright, rearrange that. K is force divided by x. Here's the next problem though, we don't have a force. So we need to work out a force, and the only force that's happening here is Sarah's weight force. Okay, so F equals mg, that's her weight force. So we're going to have 55 times by 9.8. And we're going to get 539 newtons. Okay. That's her weight force over the whole thing. What we need is a force for one spring. Okay. So all we need to do is divide the total weight force by the number of springs, 20 springs. And you're going to get 26.95 newtons per spring. Okay, so that's given us a force. Then what we need to do is to calculate our K, our spring constant. All right, so we're going to use that equation. K equals F divided by X. All right, so we're going to do 26.95, always use our unrounded, divided by this X, this distance. Now we need this distance to be in metres. Okay, so at the moment we've got 4.5 centimetres. We need to convert that into metres. So that would be 0.045 metres. Okay. What we get out of that, so this number divided by that distance, is 598.89 newtons per metre. Okay, that's our units for that spring constant. All right, we're nearly there. This is our last step. Okay, so now we have a K, we have an X, we can put that into that EP. Okay, so EP equals half kx squared. So half times our K of 598 times 0.045 squared. So we should get an unrounded answer of 0.606375 blah blah blah. All right? And that would be joules because we're talking about energy. All right, now the last step, we've got an answer, but we need to make sure that it's in the right significant figures. Okay, so let's have a look at what we've used. We've got 2 here, sort of don't really need to look at this one. We've got 2 here, definitely. We've got 3 here, and we've used 2 here for our gravity. Okay, so this is going to be in 2 significant figures because that's our lowest. So Our final answer will be 0.61 joules, 2 significant figures. So this is a merit question, okay? Even though we've got more than 2 steps, okay, they are pretty basic steps, a couple of the first ones. These steps here are the key ones, okay, and that gets us to merit. Just getting this isn't achieved, okay? Let's have a look at question D. So, when Sarah lands on the mattress after the jump, the force on her body, so on Sarah's body, is quite large. Discuss 2 changes that could be made to the springs of the mattress to make Sarah's landing more comfortable. Explain any physics principles that should be considered to make these changes. Okay, so what we're trying to do is to make it more comfortable for Sarah to land, and we need to talk about 2 changes that needs to happen to do that, okay? And these changes are to the springs, not to anything else. So we could think about it in terms of impulse, okay? So impulse is change in momentum equals force times the change in time, okay? If we're not changing the force, we're not changing Sarah's mass, so we're not changing her weight force, all right? We can have a look at changing this time, all right? And there are 2 possible ways we can do that, okay? So the first way is softer springs. Okay, so a softer material that they're made out of. Okay, this will decrease the spring constant, which is our K. All right, so if we decrease that K, the springs are able to be compressed more. Okay, so springs will compress more, increasing the time of compression. So if you can compress the springs more, it's going to take longer to do that, all right? That is going to increase our time here, all right? Momentum is going to stay the same, so force on Sarah will decrease, all right? Another option is to make the springs longer. Okay, and this will pretty much do exactly the same thing as before, okay? Decrease the spring constant, increase time of compression. Okay, so if we increase the time of compression, momentum must stay the same, so force will decrease. All right, so we need to explain that bit as well. Okay, total momentum is 0 when she lands, all right? P equals mv. If she no longer has a velocity, she no longer has any momentum, okay? So force depends on time of contact, or duration of contact, okay? The longer the time, the less force she feels, because impulse will stay the same. Okay, so that's our excellence question, all right, our predictable format in physics, all right. So for achieved, just saying either longer springs or softer springs gets you an achieved, okay. For a merit, you need one valid change, all right, so longer springs or softer springs or something else, with a correct explanation. Okay, so that's explaining that softer springs will decrease the spring constant, the springs will then compress more, so increasing the time of compression, reducing the force. Okay, and for excellence, you need both of those with the explanations and linking it all together.